Hello everyone, here we'll be talking about 8.3, which is applications to physics and engineering. And the book actually goes through a lot more detail than what I'll be talking about. They actually speak of hydrostatic pressure and hydrostatic force as well, which are very interesting topics in their own right, but they're a little beyond what I want to discuss because they're kind of technical in some sense, and they just involve too many results from physics that we probably haven't seen before. So I don't want to go off on that too much. But if you want to read on it, it's totally up to you. It's honestly pretty interesting. But here we'll be talking about moments and centers of mass. Now, just to have a basic understanding of what this means, what these words mean, is if you have two masses along a straight line that are connected by a rod, and let's call these masses M1 and M2, of course. And let's say that you want to balance it on one kind of thin point, which is known as the fulcrum. Now, it's possible that in the center is where it balances, but remember these masses probably don't have the same mass, so for that reason it's usually not going to be the center. So let's say it's something like this. Now in this case M2 would be heavier than M1, so the further away it is, the further something is away from something that's shorter, it will actually have more torque basically and be able to pull down a heavier thing. So kind of notice when you, for example, want to tighten a screw, for instance, if you have a wrench or tighten a bolt, whatever, and you have a wrench with a longer arm, you have more torque and you're able to actually provide more force, which is kind of the same as weight basically. But here we have these masses. So if we know these distances, let's call this D1 and this D2, this principle discovered by Archimedes basically says that this is at balance when M1 D1 is equal to M2 D2. Now these masses multiplied by these distances are known as moments of mass. So that's where the word moment comes from. Now the actual position where this thing is balanced is the center of mass. So let me just kind of draw the arrow again in red. So this is the center of mass. It's basically where it's balanced. So I think that's okay. Great. Now, the goal really isn't this image. The goal that we want to do in this, that we want to achieve for in this section is to consider some type of three-dimensional plate, something like that. And imagine that it may have some thickness, but we're usually going to assume that this plate is pretty thin, what is called infinitesimally thin, meaning as thin as possible, kind of. So imagine like a sheet of steel or something like that, of your favorite shape. And again, it may be some weird shape, who knows. Now the center of mass, in this case, may be somewhere, let's say, over here. Not an obvious location, but what we're going to do is we're going to find out what the center of mass is so that this balances on the fulcrum. Much like this two-dimensional image here, only now in 3 dimensions. And we can actually do that. Basically what we're going to do is imagine this image, obviously this is a 3-dimensional image here, but since it's all uniformly weighted, so to speak, let's imagine just looking at the shape itself. So let's imagine graphing the shape, something like that, on the XY plane. So let's just say it's over here, let's say, on the XY plane. Now this center of mass is just a point on the XY plane, which we can denote by X bar, Y bar. And that's actually what we're going for. We want to find X bar and Y bar. Notice that's just the location on the X axis and the location on the Y axis of the center of mass. Now, as far as physics goes, this application is called the center of mass. But as far as mathematics goes, pure mathematics, this is what is known as the centroid of a region. So if this is a region R for region, then this point right here is known as the centroid of that region. So as it turns out, centroid basically corresponds to center of mass. Now centroid may be in a different spot depending on what your shape is. For really nice shapes, you'll get really nice results. You can think of a square as just dead center. Triangle, that's something that you may want to think about depending on what kind of triangle. For instance, you can think of, let's say, an equilateral triangle where all of the sides and angles are the same, of course. But what we'll be doing is doing this kind of in general and we'll actually be able to determine the centroid of a given region. Now the given region we're going to be looking at will be defined by curves. And in fact, in this case, what this kind of tells me, just kind of looking at this, is that we'll have this top curve, let's call it f of x, and we'll have this bottom curve, let's call it g of x. That's kind of what we're going to be doing. We're going to be looking at these two curves, f and g, seeing the closed region that they define, that they kind of enclose basically. Then we can find the centroid of that region using a formula that I don't want to spend too much time developing, but in fact, I guess right now is an okay time for me to write it. But notice we can find definitely the area of this region if we wanted to. And just to remind you, let me just say this. The area of this region, let me just call it A, is equal to the integral from A to B, the most left and most right x values of the region. Let me just shift that over so we can see that better. And you can actually find A and B by setting f and g equal to each other to find A and B. And this is just, well, the top function, which is f in the region, minus the bottom function, which is g in that region, dx. Now, believe it or not, this area is always going to be positive. Even though integrals obviously represent areas under the curve, those can possibly be negative. But when you do this kind of subtraction here to find an actual area of a region, even if some of it's below the x-axis, it will always represent a positive value. What's really nice about this is that you can kind of guess. If you don't know which one's on top, f or g, well, you can just take the absolute value of this result. So in fact, this actually always holds. And let me just say where, well, I don't want to say where let me say this, where either x and a are given. So x equals a and x equals b are given, or solutions to f of x equals g of x. In other words, they're intersection points. So like in the graph I've given you here, it looks like, well, they're only intersection points. But for all we know, they could actually be given. So for instance, if we were to take a slice here and go from this line to that intersection point, then we'd have a given point A and then the intersection point B. So this is a good place to stop as far as building this up goes. And now we're going to turn to actually finding the formula for centroid, and it will involve this actually. Alright, so now here we have the formulas finally for x bar and y bar. In the case where our region is just the area under the curve of f of x between a and b, so notice here the area is just the integral from a to b of f of x. Now we're assuming here f of x is above the y-axis, but even if it was below the above the x-axis, but even if it was below the x-axis, notice that we want this to be a positive area. So for that reason, we can say it's the absolute value of this. Kind of like as I spoke of previously. Okay? And as it turns out, when you subtract 2, that'll always be positive no matter what. Now, notice the results here. So x bar is 1 over the area times the integral from a to b of x times the function, dx, where y bar is 1 over the area times the integral of from a to b of 1/2 times the function squared, dx. So this, I think, is a pretty nice result. Now, I didn't actually show the mathematics of why this is true. It comes kind of from the formula I showed of moments of mass, that is balanced when the moments of masses are equal. It also comes from the fact that the centroid is taken to be the center of mass, because since we're assuming everything's uniform, the area is approximately the weight in that case. You can kind of take them to be the same, basically. So the weight and the weight of the object, or the mass of the object, is actually well, it's dependent on the area of the object. In fact, there's a one-to-one correspondence there, essentially. Now, for a centroid of a region between two curves, f of x and g of x, well, the area here, like I spoke of previously, is this, where it's the top function minus the bottom function, and that'll always produce a positive area. But what's nice here is that if you don't know which one's on top, you can just subtract your two functions and take the absolute value of that integral, because know that that will always be a positive. So in other words, if you subtract the two functions, take the integral between the two x limits, but then you get a negative value, it means you guessed incorrectly. So that can actually give you an idea as far as which one the top one really is without even graphing, which is nice, you can do that. And you'll notice here, it's actually the same exact thing, only we have subtraction of functions now. So here x bar is 1 over a integral from a to b of x times the difference of the functions. And here y bar is 1 over the area times the integral from a to b of 1/2 times the difference of the squares of the functions. Okay, great. So when we have two functions, we'll use this. When we only have one function, we'll use this one. So it depends on our region. We'll see a few examples now, but before we move on, I want to state something. So there's a really nice result at the end of 8.3 in the book called the Theorem of Pappus, who was I hope I'm pronouncing that right. He was an ancient Greek mathematician who lived in Alexandria. And apparently he had this theorem. Oh, I don't know if it was his result or not, but it's definitely named after him. It basically says that if you want to take a region and rotate it about any line, whether it's a horizontal, vertical, or even a slanted line, just grab this region and rotate it around that line, you actually get a solid, of course, and the volume of that solid is the region, the area of the region, this guy, multiplied by the distance that the centroid travels. So notice if we're rotating, it's just going to be 2 pi times, well, the radius, and the radius will be, well, the distance between the line and the centroid of that line. And in fact, if you were to take the line to be the x-axis or even the y-axis, you get, as a result, you get the volume formulas we've seen in chapter 6. And that kind of gives you an idea as to why these look familiar, because there's a relationship there between the volume of rotation and the center of mass, as it turns out. Okay, so now finally let's take a look at some examples where we'll start to see these being used now. All right, so we have these two examples here. We want to find the centroid of the region bounded by the following curves for each of them. It's not a bad idea to graph these, so I'm going to graph these below and then we'll do the work. So for the first one, the square root of x, of course, has a graph that looks something like this, y equals radical x. And we're going to also consider the line y equals 0, which, if you don't recall, is just the x-axis. And x equals 4 is this vertical line here. So the region bounded by these three curves is what? Maybe you can see it. It's this shape right here. There we go. So first we want to find the area of this shape, and then we'll use the formula to find x bar and y bar. Now, something I want to say is that notice that here, the y value is actually the square root of 4, which is 2. I don't think we really need that though. Really notice the area under the curve from 0 to 4 of this radical is just given by this integral here. The integral from 0 to 4 of the square root of x, which is x to the 1/2. Try that a little better. Okay, there we go, looks better. And now we know the antiderivative of this is x to the 3/2 divided by 3/2, or multiplied by 2/3, and then evaluate between 0 and 4. Of course, when you plug in 0, it's just all 0, so we don't need that. When you plug in 4, well, 4 to the 3/2 is, well, 4 to the 1/2 is the square root of 4, which is 2, and then that's the third is 8. So this is going to be 8 times 2/3, or 16 over 3. So this is the area, and this is a good result, because now we can write each x bar and y bar as the reciprocal of this times that integral we saw in each of those according formulas. So I'm going to have no choice but to erase this now just for space, but I encourage you to draw this on your own and then actually plot the point we get as a result to see where it's located, and indeed that it'll be contained in this region, of course. So that, I think, is a good exercise to try that on your own, just to verify visually, basically. Okay, and now I'm going to find x bar first. Recall that x bar is 1 over this, so that's going to be the reciprocal of 16 over 3, which is 3 over 16, times the integral from the same limit, 0 to 4, of x times the function. Now notice x times x to the 1/2 is x to the 3/2, so I'm just going to combine those like that. And the antiderivative of x to the 3/2 is x to the, well, 5/2, because you add 1 to the power, divide by 5/2, so multiply by 2/5, then multiply by the 3/16 that is already there. Notice there's some cancellation here. In this case, 2 goes into 16 8 times, So we end up with this, which is really just 3 over 40 as a multiplier, and then evaluate this between the limits 0 and 4. And notice again, when you plug in 0, it's a power of x, so that'll go to 0. And when you plug in 4, remember that 4 to the 1/2 is 2, and 2 to the 5th is 32. So all in all, this is going to be 3 over, let's write it like this, 3 over 8 times 5 times 32, and we can see that 8 goes into 32 4 times, so all we have left over now is just 12 over 5. So x bar is 12 over 5. Awesome. That's another good result. Hopefully we have space for y bar. It's going to be pretty similar. Well, the formula is a little different, but the result will be kind of similar. So let's see. So it's 1 over the area, which is the reciprocal of the area, times the integral from the same limits of not x times the function, but instead 1/2 times the function squared. So that's x to the 1/2 squared. And notice when you square the square root, it cancels the power. So we just end up getting 1/2 x. In fact, we can pull the 1/2 out if you want by doubling the denominator. So it's 3 over 2 on the outside now. Integral from 0 to 4 of x dx. Now the antiderivative of x, since that's x to the 1, is just x squared over 2. Evaluate between 0 and 4. Again, plugging in 0 gives you 0, so that's fine. And then we get that times 3 over 32 still. So all in all, when you plug in 4, that's going to be 4 squared, which is 16 over 2 is 8. So this is 3 over 32 times 8. And again, we get similar cancellation we got from the above. So we get 3/4 actually. So now y bar is equal to 3/4. So now we can say with complete confidence that the centroid is the point x bar comma y bar, or 12/5 comma 3/4. And I'll leave it to you to verify that this is indeed in the region and that it looks more or less like it would be the center of mass. Great. And now this should give us a pretty good idea of what to expect for number 2. And again, we can graph this in a similar way, but I'll let you do any graphing on your own. Right now I'm going to handle this without graphing, just by kind of considering that y equals 0 is going to be the x-axis, y equals e to the x is going to be the curve above, much like we had here, and then our limits are the x values. And in fact, let me tell you right now, we're usually expected to have 2 y's and 2 x's. The 2 x's will be your limits. If you're not given those, you can find them by setting the y's equal to each other, kind of like we saw when I explained points of intersection, or when f of x is equal to g of x. That's kind of what's going on here. You can consider this y equals f of x and y equals g of x. Now, which one's on top? Well, you can actually find out by finding the area. We know e to the x on top is 0, so we don't need to do that here. But if you're not sure which one's on top without graphing, you can just find the area by taking the difference by guessing. If you get a negative, then you guessed incorrectly. And the one in front is actually on the bottom because it should have been the other way around. Anyways, the area here is going to be the integral from 0 to 1 of e to the x dx. Antiderivative of e to the x itself, evaluate that between 0 and 1, we end up getting e minus 1. Because of course e to the 0 e to the 1 minus e to the 0. So the area is e minus 1. Perfect. So that means x bar is going to be what? It's going to be 1 over the area times the integral from the same limits, 0 to 1, of x times e to the x. All right, so now what? Well, now x times e to the x actually requires, we need a dx. This requires by parts. I'll actually do this by tabular method, but I'm going to have to erase my work just for space for y bar. So let's recall that for tabular method, we need a derivative column and an antiderivative column. Now the derivative column will start with this multiplier x. Its derivative is 1, its derivative is 0. And then we take the other things multiplied and anti-differentiate this until we catch up to that 0. Then we apply the rules of tabular method, which is just multiplying diagonals like this, changing their signs accordingly by alternating, starting with positive. And what we end up with actually is x e to the x. So let me write this as, I don't know if I have space, but I'll try to write space. So this equals 1 over e minus 1 times a quantity, x e to the x, minus 1 times e to the x, just e to the x. And that's all evaluated between 0 and 1. I think that makes it on the board. Well, it's on the board, but I'm making sure it's on the screen. So now I'm going to erase the work of tabular, and now we're going to actually evaluate. Now notice when you plug in 0, you get 0 for the first term and -1 for the second because it's e to the 0. So it's going to be the first term minus -1, so it's going to be +1 actually. So let's just kind of continue here. So 1 over e minus 1. When you plug in 1, you get, let's see, you get 1 times e to the 1, which is just e, minus e. So it's e minus e for the first term, and e minus e is just 0 actually. So the first term is e minus e, but that's just 0. So really we get 0 minus that -1 that's been waiting for us. And notice really that's just +1. So really this is just 1 over e minus 1. So that's our x bar here. Perfect. Okay, so far that wasn't too bad. It looks a little weird still to me, but that's the way it is. I think it sounds good. And now let's find y bar. And y bar again is 1 over the area, so 1 over e minus 1 of the integral between the same limits of 1/2 times the function squared. Now the function is e to the x. If you square e to the x, that's just notice multiplying its power by 2. So that's really just e to the 2x. And notice 1/2 is a constant. You can pull it out if you'd like, but I'll leave it in. That's okay. So what we're left with is 1 over e minus 1 times 1/2 times the antiderivative of e to the 2x, which can be done right away. That's itself times the derivative of the inside power, which is a constant, of course, so we can pull that trick off. In other words, we gain another 1/2, so it's 1/4 e to the 2x. Then all we have to do is evaluate between 0 and 1. And notice when you plug in 1, you just get, well, e to the 2. So let me write this now as 1 over 4 times the quantity e minus 1 times e to the 2. I'll try it like this. E to the 2 minus when you plug in 0, because notice the constants you can just factor out of the subtraction basically. And then e to the 0 is just 1. So we end up getting this, which is really nice because e squared minus 1 is a difference of squares. And you can actually factor that, believe it or not, as e minus 1 times e plus 1, like that. And notice these cancel out, and you end up getting e plus 1 over 4 for y bar. So now we can say that the centroid is the x bar value comma the y bar value. So let me write it as 1 over e minus 1 comma e plus 1 all over 4. And that is the answer for this second example. And now let's move on to one more example. All right, so here we want to find the centroid of the region bounded between these two curves. And that's all that's given. So we have 2y equals, but we don't have 2x equals. And remember, our x equals values will be our limits. So we at least have our two curves, f of x and g of x. But since we're not given any other given limits, we can assume that these intersect more than once, in fact twice, and then we can find those to be the limits. So first we're going to find our limits. So let me write limits of integration by setting these y's equal to each other. Namely, I'm going to set the expression 2 minus x squared equal to x and solve from there. Now notice if you add these to the other side, you'll get 0 is equal to x squared plus x minus 2. This actually factors really nicely as, I guess, x plus 2 times x minus 1. There we go. So that implies that x is either -2 or +1. Fantastic. So these are our limits of integration. And again, it's still unclear as far as which one's on top of the other as far as graphing. I'll actually graph these after the fact. But we're going to actually just guess. I'm always going to guess first minus second, whatever's given to me, just because I don't want to think about it too much. So I'm going to write that over here actually. The area will be the integral between our limits from smaller to bigger, so -2 to 1, of the first one minus the second one. In fact, we don't even need these parentheses here actually. It's always good to write parentheses because for the second one we're subtracting, for all we know, the negative distributes, but in this case it's actually fine. And in fact, what's kind of nice to notice is that you'll actually get exactly the expression that you isolated 0 with. Well, in this case it's the opposite because we moved things to this side, but it's pretty similar. Now we can find the antiderivative of each of these terms pretty quickly. So that's 2x minus x cubed over 3 minus x squared over 2, and then evaluate between the limits negative 2 and 1, just like that. When we plug in 1, we bordered this up a bit. When we plug in 1, we get 2 minus 1/3 minus 1/2 for the first evaluation, minus, when you plug in negative 2, 2 times negative 2, notice, is negative 4. Negative 2 cubed is negative 8, so minus negative 8 over 3, which is positive 8 over 3. Negative 2 squared is positive 4, so it's minus 4 over 2. 4 over 2 is just 2. So this actually, let me see what we can do here. If we distribute the negative, we get 2 minus 1/3 minus 1/2 minus 1/2 plus 4 plus 8 over 3, I guess it's minus 8 over 3. And then it would be plus 2, but notice positive 2 and positive 4 combined to 6. So I'll just write it like that. In fact, we could have combined them already. Negative 4 minus 2 is negative 6. So that actually works out okay. Now these two actually combine to just 8. So that's 8, and then the over 3's combine to 9 over 3, which is 3. And then we have that minus 1/2 still. Okay, so it's not looking too bad. So notice that's just 6 minus 1/2. 5 minus 1/2. What am I saying? 5 minus 1/2, of course, is 4.5 or 4.5, which is the same as the fraction 9 over 2. So we have the area is positive 9 over 2. That means we guessed correctly, and in fact the first curve ends up being on top actually. And again, I'll graph this later so we can actually see that this is indeed on top and that one's on the bottom in this region between these two x values. Great. Now all we need to do is find x bar and y bar. Hopefully we have space at least for x bar, so let's see. X bar is going to be 1 over the area, so that's just a reciprocal of the area, so 2 over 9 when we say. Integral between our limits in order from smallest to biggest, so negative 2 to 1, of x times the difference of the functions. Now the difference of the functions we kind of did already, and again we want to do top minus bottom always. So top minus bottom is exactly going to give us this. So notice that's just 2 minus x squared minus x. And in fact, if we distribute that x in, let me just do that all in one shot here. We just attach an x to each of those terms. We get 2x minus x cubed minus x squared dx. And then if we take the antiderivative, let's see what we get here. Let's see, we get 2x squared over 2, which is just x squared. Which makes sense because derivative of x squared is indeed 2x. Minus x to the 4 over 4, minus x to the 3 over 3. And that's all multiplied by 2 over 9, but we're going to do the evaluation first. So now when we plug in 1, you just get all x powers replaced with 1. So that's going to be 1 minus 1/4 minus 1/3 for the first evaluation. Minus, when you plug in negative 2, negative 2 squared is positive 4. Negative 2 to the 4th is positive 16, over 4 is 4, so it's minus 4. So those cancel, which is nice. And then minus negative 2 to the 3rd is negative 8, so that's going to be minus negative 8 over 3 or positive 8 over 3. Perfect. And this is good because since we're subtracting these, that actually combines with this negative to give negative 9 over 3. And again, this is all multiplied to that 2 over 9 on the outside still, don't forget about that. Okay, so I think we have space to write it down here, so let's see. We definitely don't have space for y bar, so I'll do that after erasing. But let's see what we get. We get 1 minus 1/4 minus 1/3, and this is going to be minus 8/3. And notice 8/3 and 1/3 are both negative. They combine to negative 9 over 3, kind of like we saw previously. And 9 over 3 is just 3, so that's 1 minus 3. So we got 2 over 9 times the quantity. We've got 1 minus 3, that's going to be negative 2, minus 1/4 is negative 2.5, which is actually 9 over 4. Yeah. So we can write this as 2 over 9 times 9 over 4. It's actually negative 9 over 4, so I'll pull the negative out. That's okay. And this actually reduces quite a bit. Notice the 9's cancel, and then 2 goes into 4 twice. So we actually end up with x bar being negative 1/2. Which is okay, because negative 1/2 is actually in between these two x values. So that's not bad that we have a negative value there. That's actually okay. Okay, so now I'm going to erase a lot of this and we'll continue to find y bar and then we'll finish the problem finally. Right, so I've erased everything, and everything in black is what was given, everything in red was what we discovered previously from the previous board. And I said this is the top function, this is the bottom function. We have our limits -2 and 1. We found the area using all of that was 9/2. We found out this was top and bottom because the area was positive. Remember that if you guess incorrectly, then that means the area will be negative. So that when you're subtracting, it's actually, that would be bottom minus top in order for the area to result in negative. Okay? And x bar, as a result of all that, was -1/2. Now finally we're going to find y bar. So let's see if we can do this. So notice this is 1/a, so reciprocal of 9/2 is 2/9. Integral from smaller x value to larger x value, -2 to 1, of 1/2 times the squares subtracted. So the top one squared minus the bottom one squared. That's going to be 2 minus x squared. Oops. There we go. 2 minus x squared quantity squared minus x squared dx. Now when you actually FOIL this out, 2 minus x squared all squared is 4 minus 4x squared plus x to the 4th, and then we have a minus x squared there, like that. Now the 1/2 will actually pull out, and notice that will actually cancel the 2 on top with the 2/9 that's on the outside. So really we have 1/9 on the outside here. And now we still have the integral from -2 to 1. I kind of drew it like that so I didn't intersect these numbers too much. But that's okay. And notice these actually combine, so I'll rewrite it anyways. So this area, not area, but this y value of the area of the region of the centroid is 1/9 times the integral from -1 to 2 of, it's going to be 4. Those combine to -5x to the second plus x to the 4th. Perfect. And now, to antiderive each of these, they're just powers of x, so it's pretty simple to do, I think. So antiderivative of 4 is 4x. Antiderivative of this is -5x to the 3rd over 3. Just like that. There we go. Antiderivative of x to the 4 is x to the 5 over 5. And now finally we're going to evaluate this between the limits -2 and 1, and don't forget the multiplier 1/9 on the outside. This I think is good because when you plug in 1, notice you just get 1/9 times, for the first evaluation, we basically just get 4 minus 5/3 plus 1/5. Minus, for the second evaluation, let's see. 4 times -2 is -8. Minus, -2 cubed is -8, times 5 is -40. So that's going to be minus -40, in other words, plus 40 over 3. -2 to the 5th, well, a negative number to an odd power is negative, so it's going to be -2 to the 5th, which is 32. So it's minus 32 over 5. There we go. Now I'm going to distribute the negative here, and let's see if we can make progress in the space we have. So we have 1/9 times, let's see. So I got 4 minus -8, that's 4 plus 8, so that's 12. And then for the over 3's, notice we have -5 over 3 minus 40 over 3, that's -45 over 3. 45 divided by 3 is 15, actually. So it's -15, believe it or not. And then finally for this one, we don't get a nice number in this case. Double negative is positive, so that's 1/5 plus 32 over 5, which is 33 over 5. That's kind of unfortunate. We don't get a super nice number, but anyways, we can still combine it. Now notice 12 minus 5 is -3. So this is -3 plus 33 over 5. If we distribute that 1/9, I guess I could work in this space here. So if we distribute that 1/9, we get -1/3. 1/3. -3/9 is -1/3. There we go. And plus 33, well, it's going to be 33 over 5 times 1/9. But notice 33 is 11 times 3, so you can cancel by dividing by 3. So you really get 11 over 15. And again, that's going to be positive, so it's 11 over 15. Now this is nice because what we can notice is that we can combine these by getting the common denominator of 15 here by multiplying top and bottom by 5. What we actually end up with is 11 minus 5, which is 6 over 15. You can reduce by dividing by 3, and you get 2 over 5. Awesome. So y bar finally is 2 over 5, and using this x bar and y bar, we can finally combine them to get our centroid -1/2, 2/5. Just like that, good. And now I said I would graph this, so let's graph this and let's kind of check visually that this indeed works as the centroid of our graph. Okay, so I'm going to do my best here to graph this by hand without using any graphing calculator. Now first, so y equals x is simple, that's just a line. That's not too bad. 2 minus x squared, that's a parabola because it's quadratic. Highest power is 2. And x squared, notice, is just the parabola centered at 0, 0. Negative x squared is a facing down parabola at 0, 0. But when you add 2 to that, you shift the image up 2 units by transformations, basically. So we end up getting something like this. Try to do this justice as much as I can. And notice that it kind of passes through the x-axis here, because if you set this equal to 0, you get x is equal to positive or negative radical 2, and that's about 1.4. So I've tried to make it look like that. So this is 1 and that's 2. That's -1, that's -2. This is 1 and this is 2 on the y-axis. I think we're kind of okay. But now, of course, we want to consider the line y equals x. So notice y equals x is a line that passes through the y-axis at 0 because it's 1x plus 0. Since the number in front of x is 1, as a fraction is 1 over 1, meaning you go up 1 and over 1. So this really should be, like this is 1 right here, which looks a little more like this is 1.4. So I think I'm okay with that actually. So this is the curve y equals x. This is the curve y equals 2 minus x squared. Perfect. And now, well, okay, so we verified this is 1, 1. But can we verify that they both intersect at -2? I think we can. So at x equals -2, when x is equal to -2, y is equal to -2 from this line. But now can we confirm that the parabola also has that value, the y value, when you plug in this x value? And that's not too bad to see. When you plug in -2 here, 2 minus -2 squared is 2 minus 4, which is indeed -2. So this checks out. In fact, this tells us that this is our region here. Great. And notice it is indeed true that the parabola, the quadratic part, is on top, at least in the region between these two x values, between -2 and 1. And in fact, notice past 1, y equals x is on top of the parabola. So it's nice to see that. And now we'll do our best to actually plot this point and kind of check visually that it makes sense that it would be the centroid. So -1/2 is about right here, because this is -1, so -1/2 is halfway between them. 2/5. So 2/5 is 2/5 of the way between 0 and 1. So if you split this up into 5, you can find it that way. If you split it up into tenths, 2 over 5 is 0.4. It's going to be a little less than halfway, so something like around here, more or less. So I'm going to call this a centroid. And if you look at the image, it looks like if you had this plate and you balance it, you kind of guess to be around this point for the point of balance. Fantastic. So that's actually a good place to stop for 8.3. Really only did 2 examples, but at least I showed the formulas, of course. I think I explained pretty clearly as far as the motivation and the actually evaluation of the centroid given bounds. The only thing that I didn't really show is a sticky situation you get in where it's difficult to integrate, but in those situations you just apply the techniques we saw again in chapter 7. Kind of like we've been seeing for 8.1 and 8.2. A lot of those examples didn't really feature any of tricky integration techniques, at least not too much, because in chapter 7 we saw some pretty strange scenarios. But with a lot of these chapter 8 sections, what you'll be doing again is, given a scenario, you can apply a specific formula, like 8.1, 8.2, and 8.3, each have their own formulas, and applying the formula to the scenario, you actually get an integral as a result, so you build your own integral, and then from there you apply whatever technique is necessary. So it's very hard to tell ahead of time what technique is going to work. You have to build the integral first, and then just go from there. So I hope you enjoyed this for 8.3, and I'll see you in the next videos when we talk about more fun stuff involving calculus 2. So thanks for watching, and I'll see you then.